This is a video for AQA Further Pure Mathematics, Numerical Methods section 2.3, which is looking at the improved Euler's method for solving differential equations. We've seen in previous videos how we can solve differential equations approximately by using Euler's formula, which is based on the gradient at the start of each interval. So we're assuming at the start of this interval here, where we've got a point xr, yr, that if we can approximate the curve by a straight line, then this value here, which will be xr plus 1, yr plus 1, will be approximately equal to the actual point on the curve. As I already said, Euler's formula is based on the gradient at the start of the interval. We've also looked at the idea of using the gradient at the midpoint of the interval to be a better approximation. But there's yet another alternative which uses the idea of the gradient at each end of the interval. So if we look at the two gradients here and take the average of those, which is the dotted line, we can see that that is going to produce, in general, a better approximation than Euler's standard formula. So this method of using the gradient at each end of the interval and taking the average of those produces what is known as the improved Euler formula. Well, we have that the gradient at any point is given by the function f of xy, and therefore the gradient at the start will be f of xr yr, and at the end of the interval f of xr plus 1 yr plus 1, so that therefore the average gradient is just a half of the sum of those. If we then add yr and then h, so the interval h multiplied by that average gradient, that will give us a value which is going to be our yr plus 1. Our next y value. Now you can see that the problem with this, of course, is that as well as needing to know xr, yr, which we do know, we also need to get this one, which is the next point along. So it needs us to know the next point to use it within our formula, which seems a little bit of a conundrum, which may be impossible to solve. However, it turns out that it's not impossible, and we can show that the value yr plus 1 is given by yr is equal to a half of k1 plus k2, where k1 is given by h, which is the interval width, multiplied by the gradient at the start of the interval, and that k2 is that h, and then this is the at the end, which is xr plus h, that's the new x value, and then the new y value. However, it turns out that it's not impossible to solve, and we can show that yr plus 1 is given by this expression here, yr plus a half of k1 plus k2, where k1 and k2 are given by these further expressions here. And all of the values that we need, h, the interval width, f at a known point, so this is substituting xr, yr into the derivative, and here again in k2 we've got h, the interval width, and then this is a value of x and y that we can calculate. So by substituting the known values into these expressions for k1 and k2, we can then put those into the expression for yr plus 1. Now this is known as the improved Euler formula. You don't need to remember this, as you'll always be given it in questions. So let's look then at an example. Here we're asked to use a value of h equal to 0.1 and Euler's improved formula to find an approximation for x to y rather, when x is equal to 1.1. For dy by dx is equal to x plus root y, and y equals 1 when x equals 1. So we're starting at this point here, 1, 1, and we simply want to move along by an interval of 0.1 and find the approximation to the y value at this point here. And we'll do that by using Euler's improved formula, which is given to us. Well, the first thing we need to do then is to work out k1, which is equal to h, which is 0.1, multiplied by f of xr, yr. Now in this case, x is 1 and y is 1, so that we can substitute 1 and then 1 into the formula for the derivative, which is 1 there, which gives us a value of 0.2 for k1. K2 is then equal to h multiplied by f of x r plus h and y r plus k1. So therefore it's 0.1 multiplied by f of 1.1, 1.2. And if we substitute in the values into the differential equation, that becomes 0.1 and then 1.1 plus the square root of 1.2. And that gives a value of k2 equal to 0.2195 to 4 decimal places. We can then substitute those values of k1 and k2 into the formula for yr plus 1. So in other words, y1 in this case will be equal to y0, which is 1, plus 1/2 of k1 plus k2, so that's 0.2 plus 0.2195. And that gives a value of y 1.2098. So remember then, you won't be asked to derive Euler's improved formula. You'll always be given these expressions, so that this then is a matter of being able to substitute values that you're given in the question, the x values and the y values, into the differential equation, and then the expressions that you've got for Euler's improved formula. Well, that concludes this video, and indeed it concludes the series of videos on solving differential equations using numerical methods.